it's now that we turn back to chapter 6. We were just considering a kind of collision in which the two or more objects do not fuse or couple together and then have one velocity after the collision. And we said we needed another equation to solve that two variable system. It makes me think we need another definition. When we started chapter 8, we defined momentum, and we looked at the sort of applications of that definition and ended up with a conservation law. If we can show that the net external force on a system is zero, then the momentum of that system is conserved. And it makes me think that we need a similar thing, because we need an equal sign, right? We need a thing that is equal before and after some event. We've already talked about momentum. What other thing are we going to talk about? I'd like to talk about springs. A slinky isn't a great example of a spring. The spring that lives in, frankly, the spring that lives in a click pen is a better example. But it's a little harder to see. The spring is stuck. There we go. Oh, and I dropped it. Of course it did. The spring that lives in the click pens is a better example of spring because it has some sort of, it's not fully compressed. If you look at a slinky in like rest position, it basically exists as a cylinder. There's no gap between the spiral, between the helix, right? But one of these springs, there is. The amount of force it takes to change the length of a spring turns out, for a wide range of the behavior of the spring, turns out to depend on by how much you've changed the length already. Stretch it a little bit, it took some amount of force. Stretch it a little bit farther than that, it's harder to do. The more force, so the more stretched it is, the more it springs back, I guess, when you let go, in a certain sense. It makes me think of a rubber band that way. The more you stretch a rubber band, the harder it is to stretch it farther. I mean, at a certain point, you're stretching it so far that you're exceeding the strength of the material, and it snaps. But if you don't stretch that far, then the farther you stretch, the more you have to try to stretch farther. However fast you do it. And that's the piece that makes me curious. Whether we stretch the spring a lot all at once, or slowly over lots of time, the force that we need to do that is the same. So impulse, force integrated over time, isn't doing a good job of talking about the motion of the spring. We need to exert forces according to how much the spring is stretched, not according to what time it is, nor according to how fast we're going. I don't really care about how far, or I'm sorry, I don't care about how fast I'm going at all. I care about how far I'm going. How much am I stretching the spring from equilibrium, from its rest configuration? Not force applied over time, but force applied over distance. We, we defined impulse, J, as the integral, oops, not the sum, as the integral of force dt. We defined it that way, 3-line equals. What if there were another thing? Force integrated, it's a function of where we are. It's a function of where the end of that spring is relative to where it started. And we integrate with respect to distance traveled instead of time elapsed. What if we define that? What if we define that? Like, I'm just making shit up. That's the impulse felt pretty natural. I mean, it's just this, we move around the differential equation, we integrate both sides, and okay, the left-hand side is a thing, call it impulse. This, I don't really have a good reason to do it, except that I can kind of imagine a situation where the force doesn't depend on what time it is, but depends on where we are. It's not like there is some differential equation that I have in mind anyway when I write this. I just like, well, it worked for it worked for impulse. What if maybe it'll work for this? I don't know what this is. I don't know. What if we do it? Does it get anything useful? When we started by rewriting momentum, we weren't sure if defining momentum as mass times velocity was going to do us any good. Turns out, yes, it did, but we didn't really know that when we started. So let's let's define that and see if it does us any good. Okay, but right away I have a problem. Force is a vector, and in general, it might not only depend on the x-coordinate, it might depend on where we are. And then when we multiply by some differential displacement and then integrate, we might be talking about some vector displacement, right? Like dr in some direction. And now, how do I, wait, that's the product of two vectors. How do I do that? Sorry, I lost my marker cap. Hold on. There it goes. Oh. How are we going to multiply those? Okay. I tell you what, momentum is already a vector. We already have a vector that talks about motion. How much motion? Vector, momentum. Let's try it scalar. If it's scalar, then we want a dot product. Force dot differential displacement. Okay. I'm going to push a thing. I'm going to push a thing with a force F, 20 newtons, whatever. And I'm going to push it through a bigger displacement. Right? I'm going to push it across the room, and I'm going to push it another room farther. Pushing it farther exerts me more. I'm more tired. The farther I have to push the thing, the more effort it requires of me. Okay. What if I'm pushing a thing only across one room, but I need to use a lot more force? What if I'm using 200 newtons instead of only 20? Well, still, that requires a lot more effort of me. So this feels like a thing that tracks effort. How much effort it takes to do a thing. How much work, capital W, it takes to do a thing. The textbook starts with a definition of work in chapter 6. It doesn't tell us why. So right after chapter 5, right, when we're done talking about the applications of Newton laws and friction and air resistance and all this stuff, F equals ma, F equals ma, F equals ma, the next chapter is work is force times displacement. And it never felt at all organic to me. It just felt like a thing that I was supposed to know. And I hate those. I don't like knowing something just because someone tells me to know it. I like knowing something because it's real, right? Because it corresponds to a thing that somebody wanted to do once. Why is it this way? And then in a lot of ways, I see that as my job is to sort of explain the why. Sure, the textbook, here's the definition, work. How come? Why does it look like that? Why is it defined that way? And the answer, in my opinion, is that because defining impulse was very natural. And we needed another equation. So we made it up. We made it up so that it would look like momentum, but not be momentum. Momentum is vector. Let's talk about scalar. This is time. Let's talk about distance. We made it up, which is fine. It's a good idea. We try shit, right? And we see if it's useful. The fact that we're talking about it now sort of puts the cart before the horse a little bit. Yeah, I mean, it seems like it is useful since we're talking about it. But at the beginning, we're not sure. We try it. It's okay. Okay. Let us examine this new animal. Since it's a dot product, we know that it is force times the magnitude of the force times the magnitude of the displacement times the cosine of the angle between those two things. That's something we know. What else do we know? What are the units? Well, the units of, this is a bunch of products, force and displacement. And, well, when we had kilograms times meters per second, we called it kilogram meters per second for momentum. So when we've got newtons times meters, Newton meters. Now, the nice thing about kilogram meter per second is that it was all in terms of fundamental units. This is derived units, so it's actually kilogram meters squared per second squared, and that's just too many syllables. Let's define 1 Newton meter as 1 joule. The symbol for which will be J, which is confusing. Impulse as a quantity starts with I, and its symbol was vectored or capital J. The units were kilogram meters per second squared. This is work, not impulse. Its symbol is W, and its unit is capital J, not a vector. If you've got a J with a vector ornament, it's got to be impulse. Okay. So we can calculate work. Well, honestly, I'm not even sure what that does for us yet. Let's unpack this definition. Work equals the integral of force as a function of position. So this force could have an x component as a function of position in the I direction, plus some y component, maybe also a function of position in the j, and some z component, maybe also as a function of position. Okay. And we're going to do dot product stuff with some differential displacement, maybe some dx plus some dy plus some dz in the ijk. We know how dot products work. We multiply the i's, and I dot I is 1. F sub x, so this is the integral of everything here. F sub x as a function of r dx. We multiply I and j. I dot j is 0, I dot k is 0. The only terms that survive are the j's and the k's. Plus f sub y as a function dy plus f sub z as a function dz. Integral is distributive, so we're talking about terms that look like f dx plus fy dy plus fz z integral. Okay. Let's zoom in. Let's talk about this guy. Force in the x direction maybe has to do with the mass and the acceleration in the x direction. Now, let's assume the mass is constant. Remember, this force is a function of position, not of time. Well, wait a minute. The acceleration in the x direction is still the time rate of change. That's dvx, I guess. dt, that's by definition. That's what acceleration is. But wait a minute. So that's mass. That's all belongs to the acceleration dx. Dx divided by dt. That's the horizontal velocity. Oh my goodness. Okay. So this integrand looks like m dvx, but the dt goes with the dx and is another vx. Whoa. Okay, so we can integrate with respect to velocity. Okay, so there's some initial and some final, I guess. Let's call them V1 and V2. Equals m vx squared over 2 evaluated from V2 to V1. So I'm going to hop back up here. This was one of those integrals, the x one, and it's m v2 squared over 2 minus m v1 squared over 2. And, you know, I got to be honest, that looks an awful lot to me like the macroscopic change in some quantity mv squared over 2. Evaluate at position 2 or state 2 or condition 2 or whatever. Subtract condition 1. That's the delta. That's the change in whatever this stuff is. Now, this is Vx, I guess. So there's one of these in Vy, there's one of these in Vz. But if we kept the vector in, I think we'd end up with the same result. Oh my gosh. Okay, wait a minute. Hold on. Let me look at that. So hold that thought. This would force vector dot dr vector. Now force is mass times vector acceleration. Dr vector acceleration is dv dt dr. But dr over dt, that's v by definition. So this is the integral of m dv vector v vector. Yeah, this is, oh, wait a minute. Oh, I forgot the dot product. If I put the vectors back, I need the dot product. You gotta stop me when I do stuff like that. Dot. 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 What does that do for us? I mean, I'm sort of like, all right, dv dot v. So it'd be dv times v times the cosine of the angle between them. I don't like that at all. Maybe I was right to think about it in just x. See, this is the thing, right? We made up work, and now we got to chase through it. Okay, how does this behave? What should I do? How do I work with this? Okay. That doesn't feel great. Let me go back and talk about just x. So this was f x dx equals that. Vx2 Vx1 delta Vx. All right. But there were other terms, right? There was one for y and one for z. And the work, according to this definition, which I'm really starting to wonder if it's helpful at all, is the sum of the three. So this is the work is apparently delta mvx squared over 2 plus delta mvy squared over 2 plus delta mvz squared over 2. Now, m and 2 are constant, right? So this delta is going to be final minus initial, and then final minus initial, and then final minus initial. Each one of those terms, each one of those 6 terms is going to have an m and a 2. So this looks like m over 2 delta vx squared. So this looks like vx final squared minus vx initial squared plus vy final squared minus vy initial squared plus vz final squared minus vz initial squared. Well, that's the delta v, delta v, delta v. Let's group terms, finals and initials. So this one, and this one. Suppose we had a vector velocity. It would have some x component, some y component, some z component. If we wanted to find the magnitude of vector v, we would use the 3-dimensional Pythagorean theorem. Vx squared plus vy squared plus vz. Vf squared plus vy squared plus vz squared. Those 3 pieces are the 3 pieces here, and they're all in the final condition, as opposed to these are all final. So these arrows point to v squared final. It's the magnitude of the velocity squared without the radical, so we squared it. And oh, wait, and these 3 same thing, but with a minus sign. So if we factor out the minus sign, we end up with vx squared plus vy squared plus vz squared initial. That's the where you're right, this is completely scalar, which is good because we defined it with a dot product, so it should be scalar. But I want to come back to this idea. It was weird that it was only an x component, so I wanted to, all right, is it x only or is it y? And the answer is no, it's all together. It's the scalar velocity, it's the speed. The magnitude of the velocity here squared minus whatever it was to begin with, and that's apparently the amount of work done, right? Like I do work. The amount that something has worked. I'm not sure how to talk about it yet. Okay, so but this goes all the way back to the very first definition that we made. If we use that definition, then we have shown that it is true that this is all equal to delta mv squared over 2. And now there's no x component. It was the entire scalar speed. I feel like I've played this game before. When we were talking about we ended up with mv in a differential expression. We said, hey, let's call that a thing. Let's call that momentum. This quantity was a quantity that tracks how much matter and how much motion in what direction. This thing also tracks how much how much matter and how much motion, but it doesn't care what direction. Which, well, okay, is I guess what I said I wanted when I started. I've already got a thing that cares about direction. I want one that doesn't. We gave this a name. Let's give that a name. This equal sign is the equal sign that lives in Newton's second law, because during our derivation, we said that F was equal to ma. That's Newton's second law. This is a fantastic definition, doesn't have anything to do with Newton's second law. But once we bring Newton's second law into it, this is what we end up saying. What is this? If you're not moving, then you don't have any of it. When we were talking about friction, the friction that you have when you're moving is kinetic. I don't want to call it kinetic motion, that's redundant. I'm going to make up a word. I'm going to call it kinetic energy. This is a rock. Right there is a window. Wouldn't that be dedication, right? If I threw the rock at the window, I could break the window. See, but I don't break the window. The rock does. The rock pushes on the window. How is it able to do that? And in fact, when it pushes on the window and the window breaks, the pieces move. The pieces move as a result, as a direct result of being pushed on by the rock. They move as a direct result of being pushed on by the rock. That means the rock did work. The rock worked. How? It's a rock. How is it able to do that? It's because I threw it. If I don't throw the rock, it just sits there. It doesn't do work. It doesn't work on anything. It just sits there. It is because it is moving. Because I have caused it to move, because I have caused it to have what I'm going to call kinetic energy, that it then has the ability to break a window, make a dent in my drywall. It's only because it's moving. It is when it is moving that it has the ability to work. What is energy? It's the ability to do work. Where did the rock get kinetic energy? If it doesn't have any now, and it has some later, work was done. By whom? By whomever exerted the force to change its kinetic state, right? Whoever exerted the force to cause it to have motion, that force worked. We say that we apply or impart impulse. And we say that we do work. During the fact that I change the kinetic energy of the rock, I do work on the rock. When the rock hits the window and breaks it, the rock does work on the window. The window isn't moving, and then it is. So its kinetic energy changes. Work was done on it, the window, by the rock. Changes in kinetic energy mean that work was done. Changes in kinetic energy. Well, okay, well, now wait a minute. The window's kinetic energy changes because the rock had its own kinetic energy and I don't know, gave some of it, imparts, applies, exerts, does. Yeah, transfer, I guess. Carry over, carry through, pass on some of its kinetic energy, some of its ability to, some of its motion, and some of its ability to do work to the glass. The glass wasn't moving, is moving as a result of the collision with the rock. So the rock must have imparted, done some work. It's a rock though, and it only has the ability to do work because it's moving. If it does work, then it had better have less ability to do work. The rock stops eventually because its ability to do work is gone. It must have gotten rid of it all. It must have transferred it away from the rock to the environment, to the window, to the roof outside, to whatever the story is. Work is transferred energy. Impulse is transferred momentum. Okay. I'm convinced that this is a thing worth talking about. This is a definition of work that we made up. And kinetic energy is another thing we have to define. Kind of like we defined momentum and also defined impulse. Here we got it backwards. We defined work as the integral and then are sort of incentivized to define in kinetic energy as 1/2 mv squared, or mv squared over 2. Cool. Okay. It's an integral, which means if part of this expression is constant and we can pull it outside the integral, it's a dot product, which we know how to do. We already wrote that it has to do with the cosine of the angle between the two things. We will do an example. Well, we'll do a handful of examples, but we'll do one particular example that it might be worth looking at first before we do it. And it's the example in the textbook about your, quote, your obnoxious cousin Throckmorton. It's example 6.8. We will talk about example 6.8 together. There is only one more thing, believe it or not, that we need to talk about in chapter 6 before we can move on. And that's one additional definition. If I walk up a flight of stairs, I have to exert some force on my person to move it at constant velocity. And I undergo a displacement, which means I have done some amount of work, overcoming gravity, I suppose. What if I run up the flight of stairs instead? There's nothing about this. We don't care how much time it takes. This definition doesn't care, that by design. But I care because if I run up too many flights of stairs, I get out of breath. There's a very real, like, biological, physiological difference between doing an amount of work in this much time and doing the same amount of work in this much time. I care about the rate at which I need to do work. So it's worth defining the work done. Well, yeah, it's the rate of change of work. The rate at which work is done, the rate at which energy is transferred. Let's define that as capital P power. I'm sorry that it's a P. It is not momentum for two reasons. One, it's a capital P. Two, it does not have a vector ornament. Work and time are both scalar, so power is also scalar. Work is expressed in units of joules, we said, which means so is kinetic energy, by the way. Time is expressed in units of seconds, so power is joules per second, or we could define that as, sorry, Dad was trying to tell me something once, trying to say something to me, and I didn't understand him. So I said, "What?" And he repeated himself, and I still didn't understand him. And so I said, "What?" And he looked at me and he said, "Are you a light bulb?" And I said, "What?" And he said, "You're giving off watts." The unit of power is the watt, W-A-T-T. Its symbol is a capital W, and I'm super sorry about that. That's confusing. We've got a capital W quantity called work. Its unit is joules. We've got a capital P quantity called power. Its unit is capital W watts. It is what it is. I could tweak the definition of power a little bit, get us a different version that's useful sometimes. Suppose we do some amount of work to keep ourselves, well, okay, so we do some work. That's force dot displacement. And if you like, not delta R, but dr. So we can keep the differential. We had dw. That's differential if we talk about a very, very, very small displacement. But if we're talking about a small displacement, we're talking about the velocity. So we could write another version of the power formula as force dot dr dt is velocity. And that's all the things I need to present from chapter 6. Don't worry, we will practice. But that's the end of the theory, which is good news. There is only a little bit more. See, because we went to work in the first place, we made up work because there was a kind of collision that we didn't know how to talk about. We had momentum, but we don't have enough equations to solve the system. So what I don't have yet is a statement about what is conserved before and after some event. That's really what I'd like to talk about, so that I can bring that statement to bear on the problem of two things bouncing off each other. In order to answer that question, we need to go to chapter 7.